Yeah, hello Ketan, I'm audible.
Yes.
Okay, so today we are going to discuss about mutual inductance.
So
Actually,
yesterday, sir,
what happened?
uh, actually I left in between of the meetings because of some network issue. I didn't hear the part of the question.
Okay, I actually looked at the video like later on, so I thought you covered the complete problem and you did get the mutual inductance part because I started in the class itself, but when I see that you are not here, I left that time itself. So yeah, that was the case. Question I think we completed, right? Yeah, Ketan, did we
The
complete the problem?
omega you told, sir,
What happened?
like you told
Uh,
me to solve the omega for that question, sir.
Okay, we were left till the omega part, right? Omega, okay, I actually after that gave the value for omega and told to get the V naught itself, then we solved how to get the V naught also. Okay, let's do one thing. I have that PDF maybe, so I will be just opening that PDF once, then we'll move to this. I didn't deleted that PDF, so I'll just put it once. Yeah, okay, I'll be sharing it once. Okay, please. Okay, so Kirtna, look at this. I think I can't annotate over there. Yeah, so I told you to get the omega, but if you see in the figure itself, we figured out the omega itself. How we got this? Look, we had a comparison, like how this equation can be related with the SHM equation, this simple equation, right? So we said this part is related with this part is related with this. So we can simply say this is represented by the omega itself. So from here we said omega square comes out this much. Clear?
Yes, sir.
Okay. Also, if you could remember, we got this equation in this term, right? Till here we reached. Do you remember this part? I got all three equations in this form.
Yes, sir.
Then I said here phi is also there. So what should be the value of phi? Then I gave you the reason. I have three equations. If I know any of the first condition, do I know what is the x? I don't know. I know initial velocity of the person. That is zero at the very start. So I said just put the time is equal to zero. There's zero. You get the rest of the answer. So from here we said phi is also zero. Then I said everything we have solved in this form. You can see this. But I don't have V naught. Although here you will find it written, but I don't have V naught. How we get this? You know that what is acceleration? If you could remember, acceleration is changing with the time, right? If you go back to the equation and see, after some time you have two force on this. But if you could look at the very start, at time t is equals to zero, what is the acceleration? Because it is falling only due to gravity at the very start. So I know when time was zero, acceleration is zero. Acceleration only g. What is the acceleration formula? This one. I don't have acceleration. I know v. What is v? This is the v. So when you redifferentiate this, what you are going to get, you know v negative of v naught cos this thing you are going to get. Sorry. Okay. When you differentiate this thing, you are going to get something like something. What you are going to get? Yeah, we are going to get sorry, this will not be there. I forget this thing. When you redifferentiate this thing, you are going to get v naught omega cos omega t, right? This is acceleration part we are getting. So in this acceleration, at the time when time is zero, zero, cos zero is one. So omega v naught omega. This is at the initial. What is it equals to? Initial acceleration. What is that? G. So from here we got the value of v naught is equals to g by omega. Now you will say what is omega? We have already calculated this much. Okay, that's why. So here you can see finally the answer is written in a normal form. Like all these equations are written in the form of v naught by omega. I just wanted to make the equation looks complicated. But here at the side we have given the both value. V omega is this one and V naught is this one. So I hope this is
Yes.
clear, right? Then hereafter I started with this mutual inductance, but as you said, you were already disconnected, so there's no point of this thing. Okay, so we'll start the mutual inductance in the Fourier series. Clear? So I'll be sharing my screen. Okay, I just put my tickets. I have to share that. Sharing to connect. Configuration. All right, so I think I am audible. Okay. So look, wait now. In this chapter, whatever we did, it is a simple. Right? Previously, we discussed about the inductance itself. Something we discussed about earlier. Yeah, we discussed about earlier. Mutual inductance, self-inductance. Okay? Self-inductance is meant to say like you had a wire. Maybe, you had a wire. Current I was flowing. So you know if current I is flowing due to any point. If you look, what is the magnetic field here? Due to this magnetic field is going in this way. What if I keep a solenoid in this? This is a loop I mean. Okay, this is a loop I mean. You know, due to this wire, if I go and put a loop here, you know, due to this magnetic field will be there. So there will be some induced current, right? So this is something like like this is basically something called self-inductance. Okay, this was the case of self-inductance. In another words, I'll just make something like this is a wire and assume this is a loop. So you know, due to this current I, there is a magnetic field like this. Don't look at the direction right now, just assume. Okay, we have to assume it. Okay, now this loop also consider this part. So I'll say this is loop one, and I'm saying this is loop two. And you can also say that inductance, self-inductance of this loop one, self-inductance of loop two. Okay, this is L1 L2. Loop one, loop. Wait, have I shared this screen, Kirtana? Kirtana, is it visible to you? I'm just speaking in a very random way.
So your screen is not.
So why didn't you interpret in between? You should have told me, right, sir? Your screen is not shared.
Just now it was there, so
Okay, fine. Now I shared another screen that time. Okay, leave it fine. Okay, so that is fine. Now what if I say instead, let's remove this. Now I'll say, sir, this will also get removed. Assume I have this is a connected thing. You know, in if I just make a solenoid, if I pass a current, there will be magnetic field this way, right? This is what I'm talking about here. Okay. Here I'm saying due to this is a wire. This is a wire of current loop one. Okay. So due to this wire in loop one, you are having magnetic field like this. You're having magnetic field like this. Okay. B1 magnetic field due to loop one. In why in loop 1? Because the current flowing inside in this loop providing a magnetic field due to this loop, and this loop is this magnetic field is passing through another loop. Okay, so when some magnetic field passes some loop, this there's a flux change, right? This provides you flux change. This flux will dependent upon the value of this magnetic field, right? Okay, fine, fine. This depends upon value of magnetic field. Also this magnetic field is the cause of this current. So can I say this phi? What is the phi? Let's call this as phi 2. Why phi 2? Flux passing through this second loop. Can I say this is dependent upon current passing through loop 1? Let's call this as I1. Can I say this, Kirtana?
Yes.
Okay. Why we are saying this? Look, increase the value of current. This magnetic field is going to increase. If current magnetic field increases, flux will also get increased, right? If you do the reverse, this thing will get removed, right? But it is going to get decreased by the time. Okay. Similarly, the moment I remove it, I'm going to write it something like this: MI2. What is this MI2? This is basically called as coefficient of mutual inductance. We'll discuss this more detail. Coefficient of mutual inductance. Now, what's the point of it? Look at this. If I do a reverse now, I am saying this I1 is there. Now remove that. Now remove that I1 part. Now just say there's a wire connected with this thing, and you are having current I2. Due to this, there's some magnetic flux. Maybe I'll be using some other current. Let's do one thing. Let's change everything for the loop 2. Okay, use another color. This is loop 2, I1, I2 basically, and magnetic field passing through is this. Yellow is for the second. Okay, so if I ask you flux through, so I'll say flux through. It depends upon I1. Can I say this? Sorry, it depends upon I2. I2. This should be I2. This should be I1. 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 Okay. Flux from 2 depends upon current in the other loop. Okay. But flux in this loop depends upon the current flowing in this I1. So this I said I2. This becomes equals to Mi2. Now you'll say, sir, is it possible to have a same value? Yes. Basically, what is mutual inductance? Mutual inductance is a coefficient which is a constant value for any two loop. If I ask you on which the things this constant can depend, you should actually get an idea. What is that? That, sir, when we are talking about this loop, if I have this loop here, if I have this loop here, should the mutual inductance is high or low? When we are talking about this mutual inductance, basically the the portion of magnetic field associated with the first loop, how much it is connected with the other loop. If I say this is one loop, okay, something like this, these are the magnetic fields due to this loop. Also. What if there's another loop upside? All the portion, all the magnetic field which is connected with the first is also connected with the other one. In another case, you have one loop like this. It has some part of magnetic field in this way. Only this part is connected with other loop. So, what do you think? Which one has a higher value of m? This one or this one? What do you think, Kirtan? In which case, I can suppose to have a higher value of mutual inductance. Yeah, Kirtan, please
In the first.
respond. In the first, right? So you can think of it that if your magnetic field or link, which is linked with the another loop, which is linked with the first loop, if it is getting connected more in the other loop, then you can expect to have a higher value. Right? This is an ideation we can actually think of. Right? Fine, that is actually fine. Okay, let's think in another way. So I can also say if I increase the distance between the loop, maybe instead of here, if this loop was present here, so you can say it won't be there, right? Maybe some one part is coming if it is here. So it depends upon how much the area is there, right? Instead, if the area is less, area for the second loop is very less, right? You can say that flux is also less. So basically, M depends on multiple values. It depends upon geometry of first loop, okay? It depends upon geometry of second loop and what is the distance between them, okay? Something, something like this you can ideate. So this is a constant for you. Okay? This is a very constant which you have right now. I hope this is clear, Kirtana.
Yes, sir.
Okay. So in general, I'll be writing this way. I'll say what is M. M is basically coefficient of this. These both are not same. Okay, I'm just writing more things. So what is the unit of it? So I'll say what is the unit? Your unit is basically this is flux divided by current. This will become the same. So what is that? What is the unit of flux? Weber divided by ampere. Weber per ampere. What is the unit of flux? What is that? Mutual inductance you are supposed to know. Also, this can be represented in Henry. What is the Henry? Unit of inductance. Okay, inductor kind of thing, if you could remember, inductor has a L, right? That is self-inductance. So similarly, you are going to get it here also. Yeah, Ketna, let me know if you have any doubt.
No,
No doubt, right? Okay. Now we can actually think of discussing a bit more. I'll just write its dependency. It depends upon what it depends upon. It depends upon number of loops, right? Maybe first has more loops. Basically, all the parts which comes are geometry, right? Loops. What is the shape of loop? Size of loop. Size means to say radius, area, something. Okay. If it is a square, it can be length to get something. And relative position. What does this mean by relative position? Position and orientation. Both, both. Because what if one loop is in this way, another loop is in this way? Nothing is linked over there. What if one loop is just in this way, but another is just in this way? Only some part is connected, rest is not connected. Okay? So these things are I'm talking about. Okay? These are the dependencies on it. Okay. We don't have its derivation directly. We have basically some problems, basically a direct relation in the policy. So let's talk about there's something called there's something called reciprocity formula. So theorem, reciprocity theorem. So, so what it says, Gitna, look, when you said that due to this current I1, you had a magnetic field. Can I have it right now? Look at now. What I'm actually wanted to say is that uh, assume this color can use is it going to remove? Look at this. It's removing files. Okay, look here now. When I said you had a current I1, okay, due to this current I1, you are having some like magnetic field passing through this loop, right? What is that magnetic field? This much. Due to this presence of magnetic field, you had some induced current in this, right? Induced current. Can I say that that induced current will also provide a magnetic field in a reverse direction? Can I say this?
yes, sir.
Right? So can I say this induced magnetic field in this? Can I say if what if this gets also linked with this much, right? Because if magnetic field is there in this generated in this loop, can I say this is also going to get linked with this one?
Yes, sir.
Okay. So that's what we are actually talking about. That this is a reciprocity also. Okay. So if I ask you in this term, can I say that because we just have to we have to just make a relation between M2 and M1. Okay. So this gives you an M2 M1 relation, which says that yeah, you can see this and this. Okay, I have not actually written it as M12 or 21. Okay, in general, this must be written in terms of 12 and 21. What does this mean? This is 5. Okay, so this is 12. What does this mean? 12 mutual inductance on 1 due to 2. Okay, basically you are using the current of other loop, second loop, on first loop. Okay, this is what it is saying, and this is 2 1. By reciprocity principle, M1 is 2 is equals to M4 theorem basically. Okay, because flux 1 is equals to M12 I2 I1, flux 2 is equals to M what is it 2 1 and I2. This is something like this you are having at the end of the day. So this is directly proportional to this. This is directly proportional to this because the both are proportional. The constant which should come into the picture should always be a constant. Okay? That's why we are keeping it this way. That depends upon the geometry. So yeah, Kate, now let me know if you are clear with it. Okay, I'm just again saying we don't have a proper derivation for this. So if both are same, there is no point of saying 1 2 and 2 1. That's why if you see, I didn't write earlier in the terms of M2 1 and 2. So call it as M2 finally. Okay.
Yes.
So you can say for any pair of inductance only one term of in which M is defined. Okay. This is one more idea I can actually go with. Okay, so that's fine actually. Now if I say about the EMF, you know EMF is basically dependent upon d phi by dt. So you can actually apply this phi's. Okay, now this will become like M I1. Okay, sorry. If you put the value, you are going to get like M types of di1 by dt also. Okay, so this relation is also valid. You can apply there and get the answer in future. So I will actually try to move to some problem if I have. Okay, Kidna, so I'm giving you a problem. Look, one thing. This is part problem basically, which we may have a multiple parts. So whatever the sequence I'm going to give for this problem, you have to go in the same sequence. Okay, don't just alter the sequence, otherwise you'll get something incorrect. Okay, it will be confusing for you. You are given infinite wire. This is infinite. Okay. At some distance a, you have a loop having length L, length L, length L, length L. Okay. Do I need to do this? No. Let's change it. It will be much better. Let's call this as L and H. So what you need to do is find the coefficient coefficient of mutual inductance. Okay, now look, when you say, sir, what about the mutual inductance you're asking, what you'd have only given one loop. Just think of it. When we do this thing, for this mutual inductance, you just need current, right? Current on one, like current on this. What is the flux passing through this due to the current in this, and what is the flux passing through this part due to the current in this? So this is what we have to do. So just try to get me an answer. You had to assume currents, okay? I'm not going to give you because you are going to figure out some constant value. So you can assume some values and get the answer. Try to solve this. If you are not able to get it, please let me know. I'll explain it. Okay?
Sir, can you explain it?
Yes, definitely. Look, I'm talking about mutual inductance, right? You know that mutual inductance is something. If I can figure out what is the flux passing through this loop, if I just go back, I said whatever the flux passing into this, if okay, and if you do, sorry, there's something flux in first due to, okay, I made a small mistake. It should be two and it should be one. Okay, basically, what is the flux in one due to the current in other one? Okay, that is given. So can I say if I will make an equation having flux this side, current this side, whatever the rest constant part is, that is going to be mutual inductance. Is that clear? So for this case, if I ask you, can I calculate the flux due to this current? Assume there is a current I flowing. If I ask you, what is the flux passing through this loop? So if I ask you this thing, we already solved this problem. What is the flux passing through this loop? If you don't remember, just think of go at some random distance x, take out a small strip of dx. So what is the flux passing through this? That depends upon magnetic field. What is the magnetic field at this point? That is B, right? So B is nothing but mu naught I divided by 2 pi x. X is basically distance. So what is the flux? D phi, okay? That is going to give you Okay. Also, this is assume object 1, this is object 2. So d phi 2, that depends upon, and call it as I1 because right now I don't have any current in I2 part. I1, okay. So this comes out as flux, magnetic fields, sorry, magnetic field into area. So mu naught I divided by 2 pi x. What is area? Height into small strip dx. That gives you this. So just integrate it. The moment you do this, from 0 to phi 2 total, this integrated from 0, x is from a to a plus l, a to a plus l, okay. So this phi 2 comes out as something. What is I? This is I1, okay. Sorry, I should have kept it as I. So leave I1 one side, rest part is mu naught divided by 2 pi. This is a to a plus l, this is 1 by x, h is also there, dx. So what is the solution? You have got I times mu naught h divided by 2 pi log of a plus l by a itself. Okay, this is the solution you are going to. So if you see in this case, phi 2 is something like mu naught h divided by 2 pi log a plus l divided by a. It is going to be equals to this. So if you compare with a general equation, phi 2 is equals to m1 to I1 something, okay, please remove it. So you got m equals to mu naught h by 2 pi log of a plus l by. Understood? Okay, do one thing, take a minute, look at the problem, get the solution, look at the solution, get me your doubts, okay? We will discuss that after this. Kirtna, if you're clear with this concept, let me know. I have to give you follow-up question, okay, after this. This is first part of problem. We are going to be step-by-step problems, which will make one more problem, which is going to have a multiple subproblem. So we have solved just one subproblem of figuring out the value of mutual inductance. Now we are going to use this mutual inductance in calculating the other parts, okay? So get me the your confirmation first.
So through.
Look, now you know because there's a change in flux. Right? Why change in flux? Because that depends on current. So if I have some change in current, I will be having flux, but at the very start, you might be having. So how I can have it? So yeah, okay, now let me get to the next point. I'll just write it. If in infinite current, why I'm saying this? Because it's varying current is if infinite current, if infinite, okay, if in infinite while current is given by I is equals to I naught cos omega t. Look, now it's a very new problem. Why? When I was solving this thing, I did not consider a variation in time. Okay, I had a very constant value of current. Okay, so this is what you need to think of, right? Because if I would be keeping cos omega t, here I would also be integrating this part, but here I'm not going to so do this. So basically current is varying with the time. So we have to go a little bit one step off. You know that flux. What is the flux? We are going to get flux is nothing but if this is the case, find the EMF induced in loop. Isn't it going to be the same, right? What is EMF basically? How you're going to figure out the induced EMF? That depends on phi. So what is the phi over here? M times of phi. So you know this phi 2 is nothing but m times of this. So phi 2 is going to be m. What is I? 2 over here that gives you this cos omega. I know cos omega to be some I know. What is m? M is this big value. I'm not going to put it right now. I'll keep it at later. So if you do E is equals to minus d phi 2 by dt, negative m I naught cos differentiated becomes positive. So you will be getting sine omega t. So E becomes, what is E? Big from here to put all the values, mu naught h by 2 pi log a plus L by a times of I naught sine omega t. Is this clear case now?
Yes, sir.
It's clear. Can you figure out one mistake which we have done in this during when I was solving this problem? One very small mistake is there. If you could figure out, it would be much better for itself. Look at the differentiation of flux. Is it correct? अरे तुम्हारे C dot look, what do you think this differentiation of this is going to this much? First part is there should be positive because differentiation of cos results to sine of a negative sign. Another part, there is a coefficient of time that is omega. It is not present here, so it should also be there. So it should be omega. It should be a part as omega. These two were the key mistakes in this whole equation which I'm actually talking about. Yeah, okay, fine. Now let's go a little bit in a bigger picture. You have an infinite length, question. You can take it as an example too. Infinite length is infinite, but breadth is have a constant value that is a. Okay. From here, at some b distance, we are going to have another loop. Let's call this square. Let's not take this a loop. L and L length. Okay. So, okay, in this case, you have to figure out find M. Okay. What is this M? Mutual inductance. Now you have to figure out how to calculate it. How you are supposed to calculate this thing. So look, I'll just give you a hint how you should approach it. Two options are there. You know this flux. If you figure out flux in terms of I, whatever the rest is going to be M. So you have two options. Either figure out flux in this how due to the current flowing in this, or another way, get the current in this basically in this loop and the flux generated like flux due to this current in this loop. If you get this, you can get this M. Okay, you have two options. So either way, it's your choice. In this thing, you have to figure out which one is easier, which one is harder to get the answer. So, Kitna, can you solve this, or if I have to get the answer for this also?
I'll try.
Okay, let's do one thing. I will be giving one-sided answer basically. I just told now either you assume current in this loop and get a solution over this, or either assume current in this loop or get answer in this loop. Okay, so I'll be assuming current in this infinite loop. Assume this is current I. So you know if it's a complete rectangle, so current I is this side and I is going to get downside. Okay, this, and I'm going to say that the current in this is going to produce some flux in this loop. Okay, and then I'll going to compare. Okay, this is what I'm going to do. As a homework, you can try the reverse. Assume current in this and try to figure out the magnetic field, the flux in this. Okay, your task is to get this thing.
Okay.
Is it okay? So answer is look. What is the magnetic field due to this? You know, if this is this way, you are going this way. So if any point, if you go at any distance x, you are going to get the flux value, the magnetic field. Let's say this is basically B inside. Okay. Due to this, the magnetic field will be outside, coming towards me. Due to this, if you go at a same point, what is this length? Basically, just a second. What is this? If I'm saying this is L, what is this length? This is A plus X because this is A, right? This distance. This direction is inside. You can check out the direction. So can I say whatever the flux at this point, magnetic field you are going to get this is point. Magnetic field, you know which was greater, right? This is greater, right? So what is the net magnetic field you are going to get? That is going to be mu naught I divided by 2 pi, this bigger one A, minus mu naught I divided by 2 pi. Sorry, this is going to be actually bigger value. This is bigger, but this is smaller, right? So this is the net magnetic field you are going to get. A plus x minus A is equal to x divided by A plus x. So Kirtna, that this is the magnetic field value you are going to get at any distance x. Is that clear? Magnetic field at any distance x from this end of wire. Okay, I hope this makes clear. Now the things are the same. How to calculate flux? magnetic field into area. What is this area? If I say you are going to get some distance x, you are keeping at dx. So what is this? Mu naught I divided by 2 pi a x divided by, look one thing. This integration is harder to do as compared to this. So I will actually keep that into the previous form. Okay, this form is easier to solve. A you can not do that. So 1 by a minus 1 by a plus x. This format is easier to integrate as compared to this one. So I'll keep this in this form. So 2 pi, this is magnetic field, 1 by a minus 1 by a plus x. What is area? Look, this part dx, length is L. So this got L dx. Now just have to integrate. The moment you do though, mu naught. Okay, let's give the name also. This is flux 2 because this is second loop. Okay, loop 2, loop 1. So this is flux 2 and something. This is current, maybe I1. This is flux 2. This is small flux. Integrate. The moment you do this, you'll get complete this mu naught I1 by 2 pi inside 1 by a minus 1 by a plus x dx the whole. From where to where you are going? You are going from this x is taken from this point, right? So you are going from b length to b plus l. B plus l. So what is the integration you are going to get? Flux 2 is equals to mu naught I divided by 2 pi integration 1. Okay, sorry. Yeah, integration is like x something x by a minus log x plus a. This is the integration we are going to get from where a to b plus l. Put the value. The moment you do that, I'll take this I1 at the very end. Rest is inside 2 pi b. This is x, so b plus l by a minus keep log b plus l, subtract this b by a minus log b plus a. This whole thing multiplied by I1. I'll keep it here because I don't have space. So what's the final answer you are going to get? 2 pi. This part, attach it with this part. So 1 by a result you out b plus this result you out with this result to l by a. You are left with this and this. So this is going to result you around that when you take out this negative outside. Sorry, this was a negative. So when you do negative negative, this becomes positive. Taking negative common, L plus b plus L divided by, sorry, I kept it here. B, I had A over here. Earlier A was there, and I kept B plus L. So it should be B plus L plus A. Yeah, so it is like B plus L plus A divided by B plus A only. Alright, so that's the answer we're getting. Oh, no, sorry. You see, just from here, if you compare flux 2 is equals to M I1, so you got M is equals to mu naught by 2 pi L by A minus log B plus L plus A divided by B plus A. This is the answer, okay? Yeah, okay. So let me know if you're clear with this thing. You just look at the solution, okay, once, and let me know if you have any doubt. Clarify it here only, okay? Yeah, if you don't have any doubt, we can actually end the session by this, okay? Uh, yeah, you can let me know first.
No,
You understood this, right? So your task to do is do the reverse of it, right? We calculated, we had the first loop. Okay. Now in a homework, you have to try and opposite. Assume current in this second loop and flux in first loop. So in that way, you have to figure out the mutual inductance and check whether they are same or not. Okay, that's the only thing you have to check. So yeah, Ketna, that's all for today's session. I'll end the session by this. Okay. Hmm. Okay, do one thing. Do one more thing. If you are still in the session, yeah, do one more thing. Just take this problem. One loop, radius A, another loop, radius B. Find mutual inductance of concentric rings. Look, mutual inductance mean to say what if current is flowing, then what is the result you are going to get? Okay, this is what mutual inductance you have to figure out. It is not I'm saying that there's a current I1 is flowing and outside. You just have to assume and get the value. Okay. So that's all for today's session, Kate. Now, if you have any doubt, let me know. Otherwise, I'll end the session by this. No doubt. Okay, let's end the session. Goodbye.